here at Queens. He just very recently defended his PhD and is very quickly moving on to be a PhD graduate from Queens. So tonight you should expect a bit of a tour de force from Leo, victory lap, as you will, as he tells us about using the sounds of space-time to study our universe. Leo did a master's of math at Waterloo before joining us here at Queens, and primarily his research focuses on dissipated dark matter and trying to create dark matter versions of objects within the universe, like dark stars or dark planets. Tonight he's specifically telling us about gravitational waves, but feel free to ask him about that after the talk. So without further ado, I'll pass you over to Leo. Thank you very much.
Okay, so thanks, Lawrence, and thank you everyone for coming out. Like Lawrence mentioned, my thesis and my main research is on dark matter, which is not what I'm talking about. Possibly it's due to the trauma from writing the thesis and defending. But I'm going to be talking about something that I did do research in, and is kind of adjacent to dark matter anyways. So hopefully you enjoy this. And so I'm going to be talking to you about using the sounds of space-time to investigate or to study our universe. Now, these are kind of buzzwordy, so let's break down what that title actually means. Okay, so using the sound of space-time to study our universe. First thing, sounds of space-time. What are sounds of space-time? For reasons which you'll see in a couple of minutes, the sounds of space-time are going to be gravitational waves. Now, just as a show of hands, who has heard of gravitational waves before? Okay, a lot of people. Okay, but not everyone, which is good because then I get to talk more. Yeah, so gravitational waves are very, very exciting right now in astronomy and for reasons that we'll see. And we can use them to study our universe. What do I mean by study our universe? It means to study astrophysics and cosmology. So astrophysics, I think everyone kind of knows more or less what it is, but it focuses mainly on the research, the study of stars, planets, galaxies, etc. But then once you start zooming out and start thinking about galaxy clusters or the universe as a whole, or what the universe used to be, the evolution of the universe, the fate of the universe, this is all cosmology, which is where my main research lies. Okay, and so we're going to be using gravitational waves to think about astrophysics and cosmology. So I've sectioned this talk into a couple of sections, kind of to run you through, kind of to make sure everything is a little bit cohesive. So I'm going to start with what are gravitational waves, first of all, in case you haven't heard of it or you just need a review. And then how do we make gravitational waves? So these are the first two questions I'll try to answer. Okay, so the first question, what are gravitational waves? And so this is kind of an abstract concept that you have to introduce. But so gravity itself is a force that we all know and love, and we see every day in our lives, right? If I just jump up, it's gravity that brings me down. If I throw a ball, it's gravity that brings it down. The sun, we see the sun because of gravity. Now, Isaac Newton, in several hundred years before this guy over here, came up with a theory of gravity, and he also invented calculus, very brilliant person. But he invented this theory of gravitation, which pretty accurately describes what's going on in our everyday lives, right? So he wrote down the mathematical expressions to explain what is happening when we jump up and how we fall back down to Earth. When we throw a ball, how that falls, all of that. And so, which is pretty good. But then Einstein came along in the 1900s and proposed a very different concept, a very abstract concept, where he said that gravity is the curvature of space-time. And so what does that mean? So you can think of space-time kind of, it's like a fabric. So imagine that there was a big blanket in the middle of this room here, right? And then I were to throw a bowling ball in the middle of that. What that's going to do is it's going to start bringing that blanket or fabric down, right? Because it's heavy. And so this is kind of like what happens with space-time itself. Space-time is this sheet, and massive objects are going to curve space-time. And so that curvature is actually what gravity is. And so if I were to go and throw ping pong balls or marbles into that fabric, then it's going to spin around your bowling ball and then eventually fall into the middle where the bowling ball is. So that's gravity. It's a very unique concept, but it's one that's been tested over many years and many experiments, and it's still held up. Okay, now gravitational waves are going to be the ripples in the space-time. So if you think about that fabric, if you ever played that parachute game when you were a kid, when you sent like waves across. It's kind of like that, right? So you're sending ripples in that fabric. Another analogy you can make when you start thinking about what gravitational waves is a pond of water, right? If you have a pond of water, what makes waves normally, right? If you throw a rock in it, that's going to, boop, like splash, and then it's gonna make little waves out. And so really what makes waves and water is going to be moving or accelerating objects. And now that's true in the case of gravity as well. So me moving around and flailing my arms is actually making gravitational waves. You just can't see them, feel them, or whatever, but we're all making gravitational waves as we move. Okay? And so what makes gravitational waves? We do. Yeah, we do. But the thing is, we suck at it, which sucks, right? And you might ask why. Why is that the case? Why can't we see our own gravitational waves? Well, it's because, so imagine that you're in a pond and you throw a ping pong ball onto the water. It sends a little bit of waves, but not too big waves, right? But now if you were to somehow magically chuck an elephant into the water, then you would see a much bigger splash and much more waves, right? And it's similar for like tsunamis and whatnot. So you want bigger, heavier, massive objects. Okay? So that's one thing. Or you can move really, really fast, right? Think about jet skis. Jet skis, if you just move them slowly, they're not going to make much flares. But if you move them really fast, then you start getting that, those extra waves coming out. So the question is, what do we think makes bigger waves in space-time? And so for space-time, it's a little bit different because sure, elephants make gravitational waves as well, but they're not enough either to observe. We need to go even bigger. So we have to go bigger than elephants. And when you go bigger than elephants, you're like, okay, maybe cars. Actually, cars are smaller than elephants. Maybe like spaceships or planets or stars. And you start considering these huge astrophysical objects, which are extremely massive and black holes. Black holes. Okay, I tried. Okay, yeah, black holes. So the two objects that we mainly think about as gravitational wave sources are black holes and neutron stars. So black holes are this really, really weird object that we think exists. And we've indirectly measured it using this Event Horizon Telescope, taking a picture of the accretion disk around it. But once you're inside of this region inside the center there, no light can escape. This is an extremely compact and dense object. Now, neutron stars are also very, very compact. So they can be about the mass of our sun, but they can be the size of our Earth. So they're extremely compact, which make them excellent candidates because they're very, very massive to make gravitational waves. Okay, so I just explained this, but these are the things that are going to make the big splashes in our pond, in our gravitational pond. All right, so now I have this nice animation that kind of shows you what makes gravitational waves. So remember, an object has to move. So we have to make these black holes and these neutron stars move. Okay? And the way we look at them move in our world is we look for orbits of these things orbiting each other. And so I have this video here. Before I play it, I'm just going to describe what's happening. So those two black balls, they're black holes. This part here, so think about this as the fabric of space-time. Then near the black holes, you're going to bend space-time. What's happening? And then this thing down here is our gravitational wave signal. Okay, so I'm going to play this animation, hopefully. There's no volume, but it kind of walks you through how we look for gravitational waves. So these things are initially very far apart, and they're orbiting. As they orbit, they're going to be pretty slow, right? But then you can see now that they're starting to get closer and closer. And when that happens, their orbital speeds pick up. They start moving faster and faster. So you can't really see it, but the gravitational wave amplitude, the strength of your signal is also increasing as well. And it gets faster and faster, faster and faster. Anytime now. It takes a lot. It takes pretty long, a couple of giga years. Yeah, so until you get to this part here, they collide and then they form one big black hole. And so you can look at the signal. The signal is actually the strongest when you're over here. And then now they're just showing off with their simulation. This isn't really relevant, but you can look at just head-on collisions, which don't really happen too much, I think. But yeah, you can also do this. But now, yeah, they're just showing off. Okay, so yeah, so we want our gravitational waves, our sources to be moving very, very fast. And we want to specifically look at the part where they're merging, because that's when they're moving the fastest, and that's when everything is violent. Okay, and so now that we know how these gravitational waves are made, how do we measure these gravitational waves? So what if we're causing ripples in space-time? You know, if we can't measure it, then it doesn't mean anything. And so even though we can feel, we're technically feeling the effects of gravitational waves now, we don't notice it. But if you set up this apparatus called an interferometer, then you can go and measure this thing. And so what happens is, I'm not an experimentalist, so I'm legally not allowed in labs. But so what happens is this thing is going to shoot a laser. The laser is going to split the light and then hit a mirror there, and then come back, combine, and then recombine over. And when you're doing this, this light is going to go through a long distance there. And what happens is the gravitational wave is going to kick in and then move the mirrors and make them wobble. And when you're doing that, you're changing how these light rays are moving, or the timing at which they arrive at your detector. And then you can go and look for that signal. So that thing that I just talked about is called interference. So interference is this phenomenon where you have these two lasers, right, the two light paths, and then they meet. And when they meet, they can either combine to make a bigger signal or combine to make a smaller signal. And so here, everything is, it's like you're adding positive numbers with positive numbers and negative numbers with negative numbers. And here you're adding positive numbers with negative numbers, so you get 0. Like +2 plus -2 will give you 0. Okay, so enough talking. I'll let the animation do its thing because it's probably going to do a much better job. There. It'll be fast first, and then it'll slow it down. Yeah, wobbling mirrors, and you see now that the light's flashing because you're getting constructive and destructive interference. Now, slow motion, so the light splits, and now it's traveling equal paths, right? And then it gets bounced at the mirror, comes back, reflected again, and then they meet at your detector. But now everything is dark, there's no interference, but gravitational wave is going to come in and it's going to make these mirrors wobble. And when it does that, you're going to get this kind of on and off effect. This is a little exaggerated, but this is essentially the signal that people are looking for at their gravitational wave detectors. Okay, I'm gonna stop with it. All right, so that's cool. So now we know how to measure them. So what are the actual instruments to measure these things? And so this is a global effort to go and try to find gravitational waves. So that apparatus, that interferometer I just showed you, has been built and has actually been used to detect gravitational waves. There's 2 in the US, Hanford and Livingston, LIGO, the Laser Interferometer Gravitational Wave Observatory. There's also KAGRA, the top right in Japan, that just is the most recent addition. There's also Virgo in Italy. Virgo is not an acronym. KAGRA is the Kamioka Gravitational Wave Detector. And if you wanted to see where these are on the map, that's where they are. GEO is an older detector that people don't really talk about. And LIGO India is the one that's going to be coming up in the future as well. So another one's going to be joining this, and we're going to have 5, 6 detectors looking for gravitational waves. Okay, so I mentioned that these things actually did go and detect gravitational waves. So I'm going to play a clip for you to show you what that looks like, or rather what that sounds like. So I labeled my talk, The Sounds of Space-Time. So this is going to be, if you see that signal, that thing I talked about with the interference, you can go and transform that to an audio clip, and you can go and look for, and you can try to hear what the gravitational waves sound like. And so I'm going to show you 2 different events. One is going to be with 2 black holes that are 14 and 7.5 times more massive than the sun. So they're a bit lighter. than this pair here, which was actually the first event that we ever detected. And this one is about 30 times the mass of the sun. So they're a bit heavier, or a bit more massive. And I want you to try to notice the subtle difference in the sounds they make. Okay, so I'm going to play it now. And I'm praying that the audio works. Otherwise, I'm going to have to try to make the noises. Let's see. That's not good. Okay, so that's natural pitch, so we might not be able to hear it. Let me pause it here. So that's like what their actual sounds would be like. And maybe it might not be an audio issue, actually.
Oh, just
Okay.
and then you can check your audio.
Sorry, I'm gonna play it. Oh. Okay. Sorry, guys. Let's restaurant.
And then
MacBook speakers, right?
yeah, so like yeah, your volume is max. So it should work.
It should work.
If worst case scenario, just plug it through the MacBook.
Okay.
It'll like
Okay.
move it over the mic.
I'm not in presentation mode. I am now in presentation mode. Let's see if we can hear it. This one's supposed to be quiet anyways. You don't hear anything, right? Maybe we can hear the increased pitch one. Nope. Okay.
No.
That's not the right sound. Okay. In that case, I will try playing it on my Mac. I'm sorry. Ah,
Well, I can hold a mic while
okay. We'll try our best. Turn this to max. Okay, there you go. So this is natural pitch. They're going to modify the pitch a little bit so it's easier to hear. This is the lighter one. This is the heavier one. Lighter one. Heavier one. So they're a little bit different, right? I promise I didn't just put in bird noises. These are actually what, when you increase the pitch, that's what it sounds like. But that slight difference in audio is actually what, thank you, Nick. That slight difference in audio is kind of like how one can go and tell apart what was actually making those gravitational waves. It sounds a bit different, it takes a bit longer, it's a bit louder, etc. Now I'm actually going to do the same thing again for the other one, which is, so I talked about black holes, but neutron stars can also make, or mergers of neutron stars can also make gravitational waves, but these are much lighter. Remember, they're only about a mass of the sun, right? So listen now to what that sounds like. Let's see. Okay. I don't know if you heard it right there. It's very, very slight. But again, notice how different it is from our gravitational waves from the black holes, right? It's a lot longer, first of all. It's a lot quieter. And just like the timing of everything sounds a bit off, right? So again, this is how people can go and differentiate between what made those gravitational wave events. So this was a binary neutron star merger. And these are really, really good for multi-messenger astronomy. And so to date, this is the only gravitational wave event with an electromagnetic counterpart, which means that you actually saw some, like using just your regular telescopes, you actually saw something that followed up this event. And that's really, really useful for something I'll mention in a second. But yeah, so this was a very, very, physicists were very, very happy with this observation. And so I talked a little bit about what are gravitational waves, what makes gravitational waves. But now I just want to talk a little bit about why gravitational waves are useful. Like, why do we care? Like, okay, we get like bird noises from black holes, but why do we care, right? Okay, so what do gravitational waves tell us? So just from the sounds that you just heard and the timing of these sounds, you might be able to say, okay, maybe it tells us how big these objects were, how massive they were. Okay, sure. So that tells us a little bit about how maybe how these things could have formed, how they could have evolved, how these things could have gotten there in the first place. It also tells us, I don't have the audio clips for this here, but I'll show you a link where you can actually go and look for the, at the end, where you can go and look for the differences. But black holes can be characterized by three properties: their mass, their charge, and their spin. And so if black holes are spinning, then these are going to also affect the sounds of your thing. So this is something that you can go and look for as well. And this is a thing that I'm most particularly interested in, which is multi-messenger astronomy. So multi-messenger astronomy just means that you have several witnesses to an event. So similar to like when a crime happens, you want several witnesses so that you have multiple tellings of the same event, so you can be more confident with what happened, and you just have a more fuller picture of everything that's going on. Similarly, whenever there's these astrophysical events, you also want not just gravitational waves, but you want these things to show up in your telescope or in your neutrino detector, whatever it is you're looking for. You want multiple witnesses. Okay, and so I'm going to also talk about multi-messenger astronomy, why it's important for the research that I was involved in. So for that, so imagine that we have this picture here of the Great Lakes, right? And we're right here, okay? And now let's say that, okay, I was to ask Siri, show me the distribution of boats in the area or something. And so Siri would fill in these lakes with this, right? Now, if I then go and hide the background map, and just only look at the boats, you should still be able to get a good idea of where the water is, right? Because your boats are still kind of tracing out that water, right? Okay, that's cool. Now let's think about something else as well, fish, let's say. And then again, if I go and hide this background, then I can use boats and fishes, even though they're different objects, to give us information about where the water is, right? And so this is something that we looked into doing, which is, so this is all an analogy, where the boats are galaxies and the fish are gravitational wave events. And the water distribution is not what we're interested in. We're interested in what's called the matter distribution, which is where are all the particles in our universe? And that's important if you want to study how the universe evolved throughout time and how galaxies came to form and whatnot. Okay, and so what we have is we can use the fact that our galaxies and our gravitational wave sources are both tracing this matter distribution to learn more about the matter distribution itself. Okay, and this is really beneficial. And again, this is the multi-messenger astronomy thing that I was talking about. So you can correlate these events to give us a lot of information. So you can think about, firstly, how galaxies and binary mergers cluster together. So how close they are or how far away they are, which gives you a lot of information about maybe the environment that the black hole was formed in, or the star was formed in, et cetera. So it's important for astrophysics, but it's also important for cosmology because it tells us how our universe evolved. So it gives us important information about quantities that physicists are interested in, such as how fast the universe expands, how much dark matter is there, how much matter is there, et cetera, et cetera. So multi-messenger astronomy is this thing that I'm most particularly interested in with gravitational waves, and I think will be very beneficial to progress cosmology. Okay, so how many have we seen? So up there is a chart that kind of shows you how many objects were seen per observing run. So O1 just means first observing run, O2 is the second one. And so we went from 3,879 to 200, right? So we're on the fourth observing run now. 200 events is quite a lot. Not as many as galaxies, but still it's a lot. And so this is what the distribution of those events look like. So on the y-axis here are the masses of the black or of the objects. And so it just there's no x-axis. It's just like that to make it look pretty, I guess. And so you have these objects merging to make a bigger black hole. And so you have your black holes in blue. You have your neutron stars, very few of them, in orange. And then I want to point out that the red here are EM black holes, and the white, I guess, on this projector are EM neutron stars. EM just means electromagnetic, which means they were observed or inferred using standard telescopes. And now you see that the ones that we saw from the smaller telescopes have a smaller mass than the ones that we can see with gravitational waves. So that kind of gives us even more information about things that we could never have seen or detected before. The gravitational waves are cool in that aspect. And I also want to say, so I've been talking a lot about LIGO, Virgo, Kagra, the detectors in Japan, in the US, and in Italy, but those aren't the only gravitational wave detectors. And so there are also space-based interferometers and radio pulsar timing arrays. And you can kind of see that the landscape of gravitational waves is quite large. So you can have, we're only here, right? These are the only things that we can see, just compact binary in spirals and maybe pulsars and supernovae. But then once we have these detectors come online, then we're going to be able to see much more things that we never had access to. And there's that ominous Big Bang thing at the top, which I'll talk about in a second as well. Oh yeah, and then over here, for some reason they didn't include this, but you can also see gravitational waves in what's called the cosmic microwave background. It's the earliest possible image we have of our universe, which was measured by the Planck telescope, and just looks at temperature differences in your radio signal that you get. But yeah, so this is also a gravitational wave detector in that sense. Okay, so pulsar timing arrays, I just want to go quickly over them. So pulsars are neutron stars, which are rotating. And it's very, very dense again, and it's very magnetic. Or like there's a lot of astrophysics that go on in modeling these neutron stars. But the important thing is that they're going to emit radio waves. And we can see them from Earth. And so what you can do is you can set up a network of these pulsars, of the pulsars that are surrounding Earth. And when a very long gravitational wave passes through like this, again, it's going to change the timing that the light gets that hits Earth. And you can use that, again, that kind of interferometer idea, but not quite, to give you information about gravitational waves as well. And this is an even bigger global effort. There's a lot of radio telescopes across the globe that are looking at this. I just want to shout out the Canadian one. I think it's in British Columbia, called CHIME. But yeah, so, and then last year, 2023, so time flies, 2 years ago, there was the International Pulsar Timing Array Collaboration announced that they have very strong evidence for a gravitational wave background. So a background of gravitational wave events is different from individual mergers because it's the ones that have just been accumulated throughout cosmological history. And we can't pick out individual sources, but there's just a lot of gravitational waves that we can't associate with one single source, but we know it's from something that happened early on, right? So all of these things combined to give you one. So yeah, pulsar timing arrays are cool. That's very exciting there as well. LISA, which is the Laser Interferometer Space Antenna. In my opinion, this is going to be the pinnacle of human engineering and science, because what we're proposing for this is, think about the interferometers I talked about. There are several kilometers apart. Now we're going to go and put satellites out in space to orbit with the Earth around the sun. And these things are going to be 2.5 million kilometers, which is absolutely insane. They're going to shoot lasers in between each other, and you can use that, the same interferometer technology, to go and look for gravitational waves, which is going to be, like, I just find that crazy. Like, so if you're worried about funding, don't worry, it's Europe funding this. It was funded and it's supposed to launch in 2035, a decade from now. So let's see where we are a decade from now and hope that this heat of engineering comes on and we're able to see a lot more. Okay. Last part, I promise. talking about studying the universe, right? I want to bring it back to what gravitational waves tell us again, but this time not astrophysics, more cosmology. So our universe is old, and old as in several billion, tens of billion years old. Actually, just 110 billion years old. And so everything I've been talking about has really only been like very, very recent. Recent as in the last 3 billion years. That's your definition of recent. But if you look at the big picture, it's pretty recent, right? But there's all of this before that can also make gravitational waves, which are particularly what I'm interested in, recently at least. And so if you look back in time, you can have not just a sound or associated with a gravitational wave event, but really a symphony, a cosmological symphony of all of these different instruments and players contributing to a gravitational wave signal. So I just want to highlight some of them and go very quickly. So what are these possible instruments? So we have binary mergers again, but this time not of black holes or neutron stars, but of something called primordial black holes, which I'm interested in. So these things would have formed through some non-standard astrophysical picture. So in astrophysics, usually a star dies and then you make a black hole. But these things could have formed just due to there just being a huge amount of particles floating around. And then you can make these things very, very early on in the universe. And these things can merge, and you can see that signal possibly. There's also something called cosmological phase transitions. It's a little bit of jargon, but it just means that similar to how water freezes or ice melts, these are called phase transitions. You can also have your universe go through a phase transition itself. And then so when you do that, you might be able to see that signature. Cosmic strings are also another thing associated with phase transitions that you can go and look for, these long vibrating strings with a ton of energy. There's also Hawking radiation. So Stephen Hawking is famous for predicting this thing called Hawking radiation, where black holes are not stable objects, but they're going to evaporate their mass away and produce a ton of particles. And when you're doing that, you're also making gravitons, which are gravitational waves, so that you might be able to go and look for. There's also this thing that I used to be very interested in, which is inflation and exotic cosmologies. So inflation is this thing that really is what people think of as the Big Bang. It's what the exponential inflation is, or sorry, exponential expansion in the very early universe is, which is actually responsible for seeding all of the galaxies and stuff that we see today. So it's a very important part of our cosmology, and it's we should have gravitational waves associated with that as well in the leading models for inflation. And then there's also dark matter, which is what I work on now. Why Harry Potter? Let's see. Before that, one slide about dark matter. I'm sure you've had several talks about dark matter if you've been coming out to these observatory things. But dark matter is this thing, this hypothetical particle, which we're pretty sure is not hypothetical, exists due to the fact that it presents itself to us in various scales. So in galaxies, we see that in order to match observations and theory, we need dark matter to be hanging around. We also know that dark matter needs to be hanging around to explain very big, violent clusters of galaxies colliding with each other. And we also need dark matter to be present in the very early universe. Again, that's our first picture of the universe, the oldest picture that we can find. And we see actually that dark matter was around even back then as well. Okay. And it's important because I know that's small, but that top right thing there is dark matter. The little sliver below that is ordinary matter. So 25% of the energy matter content in the universe is dark matter. Only 5% of that are regular matter. So like protons, neutrons, me and you. Right? And there's dark energy, but we don't talk about dark matter. So it outweighs matter by quite a lot, so which is why it's important. And so what my research does now is trying to think about using gravitational waves to hear the invisible, right? So if you've all seen Harry Potter, this is the first one, Philosopher's Stone. When he puts on the invisibility cloak, he's invisible, but and you know, Professor Snape can't see him when he's sneaking around in the library. But if he makes a noise, then Professor Snape's going to know he's there. So similar like that, even though we can't see dark matter, we may be able to hear dark matter through gravitational waves. Okay, so my research, shameless plug, one slide, is that dark matter could be made up of several dark particles. So not just one dark matter particle, or maybe you have a dark proton, a dark neutron, a dark electron, a dark photon, whatever, right? If you do that, then you can actually start making dark versions of planets and stars and whatnot. And so remember, I said that stars and black holes were useful because they can produce gravitational waves. If you make them just with this dark matter, then maybe you can go and look for dark planets or dark stars making gravitational waves as well. And so if you're swimming in an ocean, imagine that you just have something that's creating waves and you don't know what it is. It's quite scary. That would be this dark matter thing. Okay. Distinguishing them is hard. So whether you have two stars merging or two dark stars merging, they're going to produce very similar gravitational wave signals. So differentiating between these events is hard, which is good for me because that means I have a job, and which is an active study of research right now. Okay, so going back to this cosmological symphony, I know that when you think about gravitational waves, it's always LIGO that's making the news. You know, it's always binary black hole mergers or binary neutron star mergers, but I just want you to go home with the message that there could be many other players as well. There could be inflation, primordial black holes, cosmic strings, whatnot. That gives you this cosmological symphony that really make the piece much more complete, the musical piece complete when you start including all of the experiments. Instruments. Okay. Okay. So my last slide is just to summarize. Gravitational waves are the ripples in space-time, and we can use them to study our universe. And for reasons that I just mentioned, the next few decades will be really exciting for multi-messenger astronomy, especially if LISA comes online in 2035. That's going to be crazy because LISA will be able to see much more than LIGO. And if you're interested in the sound of space-time that I was playing before, so the ones I played were actual events, but if you want to look at what people have done with simulations, so black holes, if one black hole is much heavier than the other, or if they have charge, or if they have spin, or if all of the different cases, then I suggest you go to this website here, where you can go and play the audio files for yourself and try to differentiate them that way. So yeah, that's it. Thank you. Raise hand. Sorry, mic over.
Thank you so much for a great talk. I was curious to see if the gravitational wave affects the regular lights around us, or to detect them, we just need to like have this very long beam kind of like light to see that pulse. Yeah. Maybe.
Yeah, thanks for the question. So gravitational waves technically do influence not just light, but everything around us. So technically, these chairs are wobbling in space-time. I'm also wobbling in space-time. But the thing is, we don't feel the effects. The reason why LIGO and those long arms feel their effects is because you have a very precise laser that's lasing across long distances, and that's going to be reflected several times. And so when you reflect it, it's not just 4 kilometers that you're looking at. You actually have over 100 kilometers